Hello and welcome to Engineering Simple. In this video, I'll talk about transformer testing and in particular load loss and impedance voltage testing. So in this slide, basically there is some terminology just to make sure that we're on the same page. So some people call load loss copper losses. That's because copper is typically used to build winding turns, especially large transformers. However, it is worth noting that some small transformers like pad mount, the ones you find by the restaurants, or pole mount, the ones that are hanging on the wood poles, etc., may have aluminum conductor. And that's because aluminum is kind of cheaper than copper. So sometimes when manufacturers optimize the design, it might be less expensive, to use aluminum than to use copper. So it's design based, but it's only small transformer. Load loss or load losses are the losses in the form of I squared R plus stray losses incurred due to applying rated current. I squared R are the losses due to conductor resistance. So, each conductor has a resistance, which causes heat, which gets dissipated in the transformer. Stray losses are the losses due to leakage flux, eddy currents, structural components like core clamps. So if we look here, this is a core. So you have one limb, two, three. So because we have three phases, that's why we have three limbs. So you have three limbs, and also you have the returns or the yokes that kind of connect the limbs together. So you have the top yoke, the bottom yoke. And what holds everything together is the core clamps. You have core clamps and you have tie rods. And different designs use different structural components. But anyway, so the purpose of using the core is to contain the flux, because when you apply voltage to the transformer, it induces voltage in the windings, which causes flux to flow through the core or in the core. But so we want most of the flux, or actually we desire to have all the flux contained in the core. However, some of it is going to leak out and will go to the core clamps, tie rods, anything that's structural, and will cause extra heat, which is part of the stray losses. So you have core limbs and you have windings. So these basically are copper turns wrapped around the core limbs. So you have copper core clamps, and you can see part of the top yoke of the core. Why do we measure load losses? Load losses may be guaranteed, and small distribution transformers with low voltage less than 600 volts are subject to DOE efficiency. So the Department of Energy in the United States, makes it mandatory to meet efficiency values. So they have like a table for each kVA. This is the efficiency value you have to meet, and they publish those, so, and you have to stamp on the nameplate that the transformer is DOE compliant. Large transformers are not subject to DOE efficiency. However, customers may specify max load losses, basically the losses not to exceed, when you do testing. Customers may ask manufacturers to quote and guarantee load losses. So when a customer wants to buy a transformer, they get a quote and they request that the competitors or the bidders basically quote load losses and guarantee them. Basically, you say, okay, this is what the losses would be, but if you get the order, then you build a transformer, and after you measure the load losses, you should not exceed the quoted losses. Otherwise, you would be subject to a penalty. So typically, it's dollars per kilowatt, above the guaranteed load losses. Load losses are required to perform heat run or temperature rise test, to determine what the temperature would be, for when the transformer is subject to the loading, or the rated load, basically. And load loss can be used as a good quality check because, manufacturers, they have a long experience, and, they build their design program based on a lot of empirical data, a lot of testing, and they should predict what the load losses should be. And if they deviate from the design or the design load losses, by a certain amount, they might know, or there is a problem and they should investigate it. So it's a good quality check. So there are a lot of reasons why load losses are measured. So how do we measure load losses? So if we assume we have a two winding transformers, obviously there are lots of types of transformers: two windings, three windings, dual voltage, uh, four windings, six windings. So there are lots of designs. But really, if you understand the basics, which is just a simple two winding, you can understand any other design type. So let's assume we have a two winding transformer that's grounded Y, grounded Y. So we have the primary, we have the secondary, or high voltage side, low voltage side. So you have one, two, three phases. You have the neutral is grounded. You have three terminals, H1, H2, H3. These are bushings. Then you have X1, X2, X3. So the rated current is circulated to the high voltage windings, and the reason being because low voltage, since it's a high voltage, it has less current. The low or the secondary or low voltage, it has low voltage, which means it has a high current. So we don't want to do that. We don't want to circulate a large current. So that's why the high voltage windings are used to circulate the rated current. Then the non-tested windings, in this case the secondary or the low voltage windings, are shorted. As you see here, here's one winding, two, three. So you short all the terminals basically. So the red color just means it's like a short, basically. It's a conductor or copper piece or whatever they use. So when you do that and you apply or you circulate a rated current to the primary side, at the same time you measure load losses in watts, impedance voltage. So either impedance voltage, it's also called short circuit voltage, or positive sequence impedance voltage. And also you measure the current circulated. Sometimes they cannot apply the full rated current. They might apply like a value that's less than a rated current, but then there are formulas you can kind of scale up to the rated current, and then you calculate the load losses and everything else, based on the ratio between the rated and the actual applied or circulated current. So after the load loss and impedance voltage values are measured, now you can correct stray losses and the resistance. Load losses, as I stated before, is nothing else but is a sum of I squared R, so the losses due to the resistance of the conductor, plus the stray losses. So when the flux leaks out of the core, the main core, it goes to the structural components like core clamps, as I showed in the previous pictures. So it causes some heat or losses. So then from this, we know that the stray losses is load losses minus I squared R. So this is measured at the test temperature. So losses measured at a test temperature Then, so for IEEE designs, if you have 65 degrees Celsius rise windings, the losses must be corrected to 85 degrees Celsius. For instance, if you measure the losses at 26 degrees Celsius, then you have to correct it to 85 degrees Celsius. See what the losses would be. Because we know with resistance, as temperature goes up, the resistance will go up. So yeah, I squared R, as I said, is the resistance, which is the losses caused by the resistance, and the resistance is measured separately. And I would recommend watching other videos that I made that talks about how to measure resistance, how to correct resistance from one temperature to the other. So the correction factor is equal to the temperature, so basically 85 degrees Celsius plus a constant divided by temperature during the test plus the constant. And the constant is 234 plus 5, 0.5, sorry, 234.5 for copper. If you use aluminum, it's 225, and I would recommend watching the videos that I made for measuring resistance and correcting resistance. It talks about this factor here. So the resistance at 85 degrees Celsius is equal to the resistance measured at the test temperature times the correction factor. Stray losses at 85 degrees Celsius is equal to the stray losses measured at the test temperature divided by the correction factor. So you can see there are two. For the resistance, you multiply by the correction factor. For the stray losses, you divide by the correction factor. So the resistance, so the takeaway is the resistance goes up with temperature. As temperature go up, resistance go up. Stray losses, however, as temperature go up, stray losses go down. So this is really what these two equations tell us here. So then once you make these corrections, so the new load losses at 85 degrees Celsius is equal to A squared R plus stray losses, both components at 85 degrees Celsius. So that's load losses. Now impedance voltage, or positive sequence impedance voltage, or short circuit impedance, because you short all terminals on the non-tested windings. So if we call Z is the impedance in percent, is equal to the measured voltage divided by the rated voltage. In one thing, you have to be consistent. If the measured voltage is line to neutral, then the rated voltage has to be line to neutral. If the measured voltage is line to line, then the rated voltage has to be line to line. So you have to be consistent. Times the rated frequency divided by the test frequency. So the rated frequency is the frequency in hertz to calculate the impedance. You want to calculate impedance at, like in the United States, it's 60 hertz, or do you want to do 180 or whatever. And the test frequency is the frequency in hertz, typically 60 hertz for the United States. In other countries, typically it's 50 hertz. However, for a 60 hertz transformer, if it's made in Europe, for instance, they might not have 60 hertz source available. They might measure it at 50 hertz, but then, using this formula, you can convert it from 50 to 60 hertz. So note that impedance is the square root of reactance squared plus resistance squared. So this symbol here is just square root. So X is reactance in percent, which is the square root of impedance squared minus resistance squared. R is just resistance in percent, which is equal to a load loss in kilowatts divided by rated kVA times 100%. And again, anytime you have units, you have to be consistent. Load loss, if you measure it in watts, then you have to do VA. If you measure load loss in megawatts, then you have to do rated MVA. So you have to or multiply by the right unit, just so for consistency. Otherwise, you're going to be off in your calculation. So here's an example. If we assume we have a transformer that's rated 27/36/45 MVA, also known as ONAN/ONF. So basically it has three ratings. So 27 MVA just means no fans are on, no pumps, nothing. Then 36, it just means one stage of cooling is on. Fans basically, 45 MVA, it just means all cooling stages or cooling fans are on, fans or pumps, and so on and so forth. So the high voltage is 130 kV, 138 kV, grounded Y, and it has copper windings. Low voltage is 13.2 kV, grounded Y, and it has copper windings. The load loss penalty is $1,300 per 1 kilowatt if it exceeds 100 kilowatt at 27 MVA. Typically, load losses are guaranteed at ONAN or base MVAs. In this case, 27 MVA. So let's assume we measured these values at 23 degrees Celsius. So line to line or line to neutral voltage is 9.41 kV. And if you want to find the line to line, you just multiply this value by square root of 3 or 1.732. The load losses were measured at 89 kilowatts. So this is the total load losses of all three phases. The high voltage average winder resistance is 1.0064 ohms per phase, per winding basically. It's not line to line. Low voltage average winder resistance is 0.008462 ohms per phase. And if we want to calculate the high voltage rated current is 27 MVA divided by square root of 3 or 1.732 times 138 kV, which is 112.96 amps. You do the same thing to the low voltage and you get 1180.98 amps. So now we're going to perform calculations at test temperature, which is 23 degrees Celsius. So impedance Z is equal to the measured voltage 9.41, which is line to neutral, times 1.732 kV divided by 138 kV. Sorry, there's a typo here. This should be 1.732 divided by 138 kV because we know this is line to line. That's why I'm converting this from line to neutral to line times 100%, which comes to 11.81%. Or if you want it in per unit, it's 0.1181 per unit. This is at the test temperature. Resistance is load losses. In this case, we measured 89 kilowatts divided by 27,000 kVA. So we have to be consistent. This is kilo. This has to be kilo. That's why I'm converting 27 MVA to 27,000 kVA times 100%, which comes to 0.33%. Reactance from the previous equation is the square root of impedance squared minus resistance squared. So if I plug in the numbers, I get 11.805%. So the high voltage I squared R, so this is the total, 3 because I have three phases, times the current in the high voltage windings is 112.96 squared times the per phase resistance, which is 1.0064, which comes to 38.52 kilowatts at 23 degrees Celsius. I would note here that I multiplied by 3. That's because I used a line to neutral resistance. If I used line to line or phase to phase resistance, I would do 1.5 instead. So if you watched some of my videos that I made, I multiply, I do 1.5 times I squared times a line to line or phase to phase resistance. The difference here, or the reason I'm multiplying by 3 instead of 1.5, is because I am multiplying by the phase to neutral resistance. So if I do the same thing to the low voltage, I plug in all the numbers, I get 35.4 kilowatts. So stray losses from the previous equation is load loss minus the total I squared R. So I measured 89 kilowatts minus I squared R in the high voltage plus the I squared R in low voltage, which comes to 16.08 kilowatts. This is at 23 degrees Celsius. The correction factor, since I'm using copper, so I want to correct the losses to 85 degrees Celsius. So it's 85 plus 234.5 divided by the test temperature, which is 23 plus 234.5, which comes to 1.240777. If the high voltage had copper, low voltage had aluminum, then you have to calculate another correction factor for aluminum. And instead of using 234.5, you're going to use 225 here and here. So now let's calculate the corrected load losses. So the high voltage I squared R now at 85. So the correction factor times the I squared R at the test temperature. So it comes to, so you can see it went up from 38.52 to 47.79 kilowatt. I do the same thing for low voltage. I get 42.68 kilowatts. So that is stray losses at 85 degrees Celsius. As I stated before, for I squared R, or anytime you have resistance, you do the correction factor times. For the stray losses, however, you divide by the correction factor. So if I want to calculate the stray losses at 85 degrees Celsius, I take the stray losses at the test temperature, which is at 23 degrees Celsius, which is 16.08 divided by the correction factor. So you can see it went down from 16 to, say, 13. Now, the load losses at 85 degrees Celsius is the total I squared R, which is, you have high voltage and low voltage, so 47.79 kilowatt plus 42.68 kilowatt, plus the stray losses at 85 degrees Celsius, which is 12.96 kilowatts. So the total is 103.43 kilowatt. If you remember, at 23 degrees Celsius, we measured 89 kilowatts. So you see it went up because of resistance. So in this case, we see that measured load losses exceed the guaranteed value by 3.43 kilowatts because the guaranteed load losses are 100 kilowatts. So a penalty would apply. So you take the extra load losses, which is 3.43 kilowatts, times the loss formula or the penalty, which is $1,300 per kilowatt. So if you do the math, it's $4,459 will be credited to the customer, basically. So then the resistance at 85 degrees Celsius is, if I want to find the resistance in percent, I take the load loss at 85 degrees Celsius, which is 103.43 kilowatt, divided by the rated kVA, which is 27,000 kVA times 100%, which comes to 0.383%. So the impedance at 85 degrees Celsius is the square root of x squared plus r squared. So reactance squared plus resistance squared, which is equal to this value here, which comes to 11.81%. So as you see here, the only term that gets corrected for temperature is resistance. So the reactance that is not temperature dependent, it's only resistance. So that's it for load loss and impedance voltage. So if you want to watch more videos, I would recommend you go to Engineering Simple. So there are many videos out there. Thank you and have a great day.